Physicists assert that the universe had its origin in a monumental event known as the Big Bang, which occurred approximately 13.7 billion years ago. This event is thought to be the starting point of all matter, energy, space, and time as we know it. According to the prevailing scientific narrative, the Big Bang marks the birth of the universe, where an infinitely dense point, often referred to as a singularity, suddenly expanded, releasing an immense amount of energy that eventually led to the formation of galaxies, stars, planets, and all other cosmic structures. However, a question that continues to intrigue both scientists and the general public alike is what exactly caused this explosion and why it occurred in the first place. Despite the vast amount of research and theoretical work dedicated to understanding this event, the precise cause of the Big Bang remains one of the most profound mysteries in cosmology. Over the course of many years, researchers have delved deeply into the science and history of our universe, with the Big Bang theory emerging as the predominant explanation for the phenomena we observe in the cosmos. This theory has been supported by countless studies and the collective efforts of thousands of scientists who have gathered data that consistently aligns with the idea that the universe began with this explosive event. According to this theory, a mysterious force known as dark energy, which is even more abundant than galactic energy, plays a crucial role in the ongoing expansion of the universe, a process that has continued ever since the Big Bang occurred. The field of science today is vastly different from what it was in the past, thanks to significant technological advancements and the development of new theories. As our tools and methods for observing and understanding the universe have evolved, so too have our ideas about how the cosmos functions. Many times, these new discoveries have led us to realize that concepts we once believed to be absolutely true are, in fact, far from certain. For instance, the renowned physicist Michio Kaku has recently brought attention to new evidence that challenges the traditional understanding of the Big Bang. This shift in perspective is largely due to the groundbreaking observations made by the James Webb Space Telescope, JWST. The JWST has detected 750 new galaxies that do not resemble what scientists had expected to find based on existing models and theories. These unexpected findings have opened up a new line of inquiry, prompting researchers to reconsider how the James Webb Telescope is fundamentally changing our understanding of the universe. As we embark on this incredible journey beyond the far reaches of the observable universe, we are likely to uncover even more details about the vast number of new galaxies that have been discovered. For those interested in staying informed about the latest developments in our understanding of the universe and its surroundings, subscribing to channels and sources that provide regular updates is highly recommended. Additionally, engaging with content such as this by liking, sharing, and turning on notifications can help spread knowledge and foster a greater appreciation for the ongoing exploration of the cosmos. The images of new galaxies captured by the James Webb Space Telescope are nothing short of breathtaking. In a single photograph, hundreds of galaxies can be seen clustered together, showcasing the immense scale and beauty of the universe. The sheer power of these images is enough to leave anyone in awe, highlighting the extraordinary capabilities of modern astronomical instruments. However, while these images are inspiring to the general public, they have a different, more complex significance for researchers. For scientists, these images are both fascinating and puzzling because they do not match the predictions made by existing cosmological theories. In fact, the number of galaxies being observed is far greater than expected, and these galaxies possess characteristics that set them apart from others. They are smaller in size than previously imagined and exhibit a truly remarkable age, suggesting that they formed much earlier in the history of the universe than current models would predict. These surprising findings are causing a stir in the scientific community, with some researchers even expressing a sense of panic. The seriousness of the situation is underscored by the fact that an article discussing these discoveries began with the word panic in its title, signaling just how much these observations challenge the established understanding of the universe. According to long-standing theories, particularly the Big Bang theory, the origins of our vast universe can be traced back to a single mysterious cosmic event that occurred around 13.7 billion years ago. However, the new images captured by the James Webb Telescope challenge this narrative by providing evidence that contradicts key aspects of the Big Bang hypothesis. These images, which reveal galaxies that are too small, smooth, old, and numerous compared to what the Big Bang theory would predict, are prompting scientists to reconsider the foundational principles of cosmology. The fact that these galaxies are 2 to 3 times smaller than similar galaxies imaged by the Hubble Space Telescope is particularly troubling because it defies the expected behavior in an expanding universe. According to the Big Bang hypothesis, as the universe expands, objects should appear larger as their distance increases. However, the observations made by the James Webb Telescope show galaxies that do not conform to this expectation, leading to a reevaluation of what we understand about cosmic expansion. Moreover, the smoothness of these galaxies is another unexpected feature that challenges the Big Bang theory. According to the theory, galaxies should exhibit irregularities and variations in their structures due to the dynamic processes involved in their formation and evolution. These processes, which include the gravitational interactions between galaxies, the influence of dark matter, and the ongoing star formation within galaxies, should result in complex and varied structures. However, the images from the James Webb Telescope reveal galaxies that are unusually smooth, lacking the level of complexity and roughness that would normally be expected in galaxies of their age. This finding is particularly significant because it suggests that the time sequence for the formation and evolution of galaxies, as predicted by the Big Bang theory, may not be accurate. If these galaxies are as smooth and uniform as they appear, it could imply that the processes that shaped them were different from what current models suggest. At the beginning of the universe, according to the Big Bang theory, all matter, energy, and the fundamental building blocks of the cosmos were compressed into an extremely concentrated point known as a singularity. This singularity is thought to have contained all the mass and energy of the universe in an infinitesimally small space, resulting in an extraordinarily high density. The concept of a singularity is grounded in our current understanding of the laws of physics, particularly the equations of general relativity proposed by Albert Einstein. These equations describe how gravity operates on a cosmic scale and how matter and energy influence the curvature of spacetime. Within the singularity, the density of matter and energy would have been so extreme that the laws of physics as we know them might not apply in the usual way. This extreme density also implies that the temperature within the singularity would have been unimaginably high, far exceeding any temperature observable or reproducible in our current understanding of the universe. The energy stored in this hot, dense point is believed to have been the seed from which the entire universe, as we know it, originated. This singularity marked the beginning of everything in our cosmos, from the smallest particles to the largest galaxies. Following the initial singularity, the universe began its expansion in a process known as cosmic inflation. This phase of rapid expansion is thought to have occurred within a fraction of a second after the Big Bang and is responsible for the large-scale structure of the universe as we see it today. During cosmic inflation, the universe expanded at an unimaginable speed, far exceeding the speed of light, which allowed it to grow from a tiny, dense point to a vast expanse of space in a very short amount of time. This expansion is often described as the stretching of the fabric of space itself, pulling everything within it along for the ride. Cosmic inflation played a crucial role in smoothing out the irregularities in the early universe, homogenizing the distribution of matter and energy, and setting the stage for the formation of galaxies, stars, and other cosmic structures. As the universe continued to expand, the rate of expansion gradually slowed down, leading to the more measured pace of cosmic expansion that we observe today. It is important to note that although the initial phase of inflation was extremely rapid, the universe has continued to expand at a steady rate over the past 13.7 billion years. This ongoing expansion is known as cosmic expansion or the expansion of the universe, and scientists have observed its effects through various phenomena, such as the redshift of light from distant galaxies. Redshift is a key piece of evidence for the expanding universe, as light from distant galaxies travels through space, and the expansion of the universe stretches the wavelengths of this light, shifting them toward the red end of the spectrum. This phenomenon, known as redshift, indicates that galaxies are moving away from us, providing strong evidence for the ongoing expansion of the universe. During the early stages of this expansion, all the matter that makes up our universe was compressed into an incredibly small volume. In such a compact space, matter as we know it could not survive, leading to a series of transformations that eventually gave rise to the familiar particles that make up the universe today. As the universe expanded and cooled, subatomic particles such as protons, neutrons, and electrons began to form and interact with the light and energy around them. These interactions played a critical role in the formation of matter in the universe during the first few minutes after the Big Bang in a process known as nucleosynthesis. Initially, scientists expected to observe chaotic and disrupted galaxies shaped by multiple collisions and mergers, which were thought to be a common process in the early stages of galaxy evolution. However, the images captured by the James Webb Space Telescope tell a different story. Instead of chaotic, disorganized galaxies, the images reveal well-organized disks and spiral structures that closely resemble the galaxies we see in today's universe. This unexpected observation challenges the long-held idea that mergers are a dominant process in galaxy evolution. If these new galaxies have not experienced many or any mergers, it becomes increasingly unlikely that small galaxies would grow and evolve into the massive galaxies we observe today, as the Standard Model suggests. This implies that these galaxies were never small to begin with, but rather formed in a more organized and stable manner than previously thought. Furthermore, the optical illusion predicted by the expanding universe hypothesis, where objects appear smaller due to the expansion of space, does not seem to apply in this case either. The fact that these galaxies do not conform to the expected patterns of size and structure raises serious questions about the validity of the Big Bang theory and the broader understanding of cosmic evolution. In addition, the age and abundance of galaxies revealed by the James Webb Space Telescope also pose significant challenges to the Big Bang theory. The JWST is equipped with advanced filters that allow it to capture images in the infrared part of the spectrum, which is crucial for studying the colors of distant galaxies. By analyzing the colors of these galaxies, astronomers can estimate the age of the stars within them and the galaxies themselves. However, the findings from the JWST suggest that these galaxies are much older than previously thought, and their sheer number far exceeds what the Big Bang theory would predict. This discovery is particularly troubling because it suggests that the universe may have been populated with fully formed galaxies much earlier than the theory allows for. As we continue to explore and analyze these new observations, it becomes increasingly clear that our understanding of the universe's origins may need to be revised. As we delve deeper into the revelations brought forth by the James Webb Space Telescope, JWST, it becomes clear that our understanding of the early universe may be on the brink of a paradigm shift. One particularly intriguing aspect of these new findings is the potential impact on the timeline of cosmic events. Traditionally, cosmologists have relied on the Big Bang theory to explain the sequential development of the universe. However, the unexpected characteristics of the newly discovered galaxies suggest that the formation and evolution of the universe might have occurred in ways that diverge from the conventional models. One area of significant interest is the nature of the early universe's structure. According to established theories, the universe's earliest stages were characterized by a highly uniform and homogeneous distribution of matter. Over time, slight variations in density would have led to the formation of the first structures, such as galaxies and clusters of galaxies. However, the discovery of these newly imaged galaxies, which appear unusually mature and complex for their purported age, raises questions about the accuracy of this model. These observations challenge the idea that the early universe was dominated by a relatively smooth and featureless expanse. The new data from the JWST also suggests that the process of galaxy formation may have been influenced by factors not fully accounted for in existing models. For instance, the presence of numerous well-formed galaxies at such an early stage could imply that mechanisms beyond those currently understood played a role in their development. Some researchers are exploring the possibility that dark matter, which is thought to exert a gravitational influence on visible matter, might have had a more significant impact on galaxy formation than previously recognized. If dark matter's role was more pronounced in shaping early structures, it could provide a new perspective on how galaxies formed and evolved. Another aspect of these findings involves the nature of cosmic reionization, a critical phase in the universe's history when the first stars and galaxies formed and emitted light that ionized the surrounding hydrogen gas. This period is crucial for understanding how the early universe transitioned from a neutral state to one filled with ionized hydrogen. The surprising characteristics of the newly observed galaxies could offer new insights into this process. For example, if these galaxies were indeed forming and shining earlier than previously thought, they might have played a more substantial role in the reionization epoch than current models predict. Additionally, The JWST's ability to capture images in the infrared spectrum has provided researchers with a wealth of new data about the universe's earliest objects. By analyzing these infrared images, scientists can peer through the cosmic dust and gas that often obscures more distant and earlier galaxies. This capability has allowed for the observation of galaxies that are both older and more numerous than previously estimated, offering a new window into the universe's infancy. The ability to detect such distant objects challenges existing theories about the visibility and detection of early cosmic structures. The implications of these findings extend beyond the realm of cosmology. If the characteristics of the newly discovered galaxies significantly deviate from established models, it may necessitate a reevaluation of other fundamental aspects of physics and astronomy. For instance, the understanding of how galaxies interact and merge could be altered, leading to new theories about the dynamics of cosmic structures. This, in turn, could affect our comprehension of galaxy evolution, star formation, and even the formation of large-scale cosmic structures such as clusters and superclusters. Moreover, these discoveries highlight the importance of continued observational and theoretical advancements in cosmology. As technology progresses and new instruments like the JWST come online, they provide opportunities to test and refine existing theories. The discrepancies between observed data and theoretical predictions underscore the need for ongoing research and openness to new ideas. The scientific community must remain agile, adapting to new evidence and integrating it into a coherent framework that enhances our understanding of the universe. The next steps in addressing these challenges will likely involve a combination of further observational studies and theoretical modeling. Researchers will need to investigate the newly discovered galaxies in greater detail, examining their properties and distribution to better understand their implications. Additionally, cosmologists will need to develop new models that incorporate these findings, potentially leading to revisions in the Big Bang theory or the development of entirely new theoretical frameworks. In conclusion, the James Webb Space Telescope has provided a treasure trove of data that challenges our current understanding of the universe. The unexpected properties of the newly observed galaxies prompt a re-examination of existing theories and open up exciting avenues for future research. As scientists continue to explore these revelations, they may uncover new aspects of the universe's history, leading to a more refined and comprehensive understanding of cosmic evolution. This ongoing journey of discovery is a testament to the dynamic nature of science and its ability to adapt and evolve in the face of new evidence.